h over 2 and put one of those on each side of the A. So this kind of regulated correlator has appeared in various contexts, and it will turn out to be useful for us here. Notice that, in things like quantum field theory or something fancier than spin systems, products of operators tend to be singular and so on. So throwing in this helps regulate it, which is why I'm calling it the regulated correlator. Okay, so the goal is to show how this is related to the F function. And so we write the trace as a sum over energy eigenstates. And then somewhere here, I think we put in another complete set of energy eigenstates. And then, and I left out the sums. Okay, so we just get that, and I neglected to say up here, again, that E is the average energy, and omega is the energy difference. And so by splitting up the e to the minus beta h, we just get the central energy E. And this is omega. And this is e to the minus s of E. But now I have Rij squared, and so as I do the sums over I and j, that's just going with times these smooth functions, that will just give me the statistical average, so I can just replace Rij squared by 1. And then these sums, if I look at a particular one, I want to change the sum to an integral, but as I change it to an integral, I will need to include a density of states factor, e to the s. So I get this, and I get one of those for I and for j. Okay. So now we have these entropies S of E at different energies. We have one at EI, we have one at EJ from the other sum, and we have, by definition, an e to the minus s of E at the intermediate E here. So if we look at, so now what I want to do is Taylor expand this about E. Well, remembering the definition of E and omega up there, this is half omega. And then remembering thermodynamics class, the derivative of the entropy with respect to the energy is the temperature, or in beta notation, 1 over beta. This basically follows from dE is TdS. And the second derivative is minus beta squared over C, where C is the heat capacity. And this takes a little more work, but the basic relation is that differential of energy is the heat capacity times differential of temperature. So I claim if you mess around with those differentials, you can derive these two formulas. Okay, and C, the heat capacity, we can see it from here. E scales like N. Temperature does not scale with N, and so we should think of the heat capacity as scaling with N as well. Okay, and so if we then repeat this for Sj, and let's see, we're going to want to, so we're going to get an S of EI, we're going to get an S of EJ, and we've got a minus S of E here. And so that will become S of E. The linear terms in omega cancel, and if I've done this right, this is beta squared omega squared over 4c. And in principle, we could, of course, keep going. I'm sorry? Yeah, so this is the combination. This combination is what we're going to get up here, because we have this, and we similarly have sum on J, and then we have a minus S. But S of EI starts out at S of E, and so does S of EJ. So I get two of those, minus one of these, and I have one left over. All right. Also, it will be useful to change the two differentials to differentials over E and omega. Okay. And all right, so having done all that, maybe I can still write up here. Okay. So we plug all that in. And we get this. All right, and now I've cheated a little bit because I extended. Sorry.
The omega should be bounded by plus E minus E.
Right, right. So, right, I was just about to say that.
Okay.
So right. So secretly, the omegas are bounded, but I want to think of omega as a number of order 1, which, because I want to think of times of order 1 and betas of order 1, so the natural thing here is of order 1. And so really, this is some number that scales like, you know, I don't know, min or max, whatever. And similarly, something like that. But these are of order n, and so I'm going to scale those off to infinity. But you're right that really there's a cutoff. But the cutoff is of order n. And at order, if I set omega to be order n, here I'm going to get an n squared in the numerator, and I'm going to get a c, which is order n in the denominator. So this term will be e to the minus n by that point. So that's going to cut off my omega integral anyway, so I can extend it to infinity. And now I'm going to go ahead and set c to infinity and basically ignore this factor. So in the thermodynamic limit, and I'm going to rely on f, the behavior of f to make this function convergent, and as we'll see in a minute, that will have to be the case. Okay, so over here we still have an integral over e, but again, e and s are both of order n, so I can do this integral by, I call it steepest descent. Chaitanya Murthy, my collaborator, insists that it should be called Laplace's method when e is real. So by Laplace's method, we evaluate this as evaluated at the solution, at the stationary solution point. Okay. All right. So I guess I should say at the solution of. Okay. But that, the solution of this is just the thermodynamic relation between energy and temperature. And furthermore, what this is, in this same approximation, this is just the path, the partition function. Right? Trace e to the minus beta h with the trace written as an energy integral. Okay. So the answer is this integral just cancels the 1 over z we put in at the beginning. But now over here, we should understand E as having been fixed by the thermodynamic relation between energy and temperature. And this is all in the context of steepest descent or Laplace's method, where we don't worry about prefactors in the exponential of the large thing. Okay, so that's the answer.
Excuse me, what about the F? The F also depends on E, right?
In this context, beta is fixed at the beginning. Well, I just erased it, right? But the beta is fixed because the thing we are computing, by definition, has an e to the minus beta h in it. So, yeah, I didn't really explain this very well. But here, beta is now an input parameter because I've decided I'm going to compute this object. Okay. And so now E is determined by beta by the usual relation.
Sorry.
Yeah.
The left-hand side shall not be F2T average, the average for the Rij coefficients. You use it that Rij square equal to 1.
Yes.
So the F2 should be average also.
Right. So the idea is, right, when I write down. The bus, okay. If anybody needs the bus, now is the time. Okay, so the idea is that these functions are smooth functions of these quantities. The actual energy levels are extremely dense. The spacing is e to the minus s. So the idea is if I look in some range of energy, I have many, many levels over which these functions are essentially smooth. And so I want to think of Rij. I want to fix a range, I don't know, from e to e plus delta e, where delta e is small on the scale at which these functions vary, but still encompasses many, many levels. And so I want to say that Rij averaged over this set of levels is 0, and Rij squared averaged over this set of levels is 0. 1. Thank you. Right. But I don't have to worry about f because there's so many levels over which f is effectively constant. So that's the idea. Okay. Where was I? All right, so we're basically done. The answer is, after we've done all this, all right, again, this is now in a limit where I can think of n as large enough that I can throw away this factor, extend these limits to infinity, and so on. So this is the punchline. The f function that appeared mysteriously in the matrix elements. It's the Fourier transform of its square is this regulated two-point correlation function. So okay. The phase has no physical meaning. In a system that's time reversal invariant, everything here is real. It's theoretically possible for this to change sign, but it doesn't have a phase, and at least in that case. And furthermore, it's also you can in that case it's also you can show it's an even function of omega in the real case. So okay. Now there's something else we can do here, which is formally consider an imaginary time. So I guess, all right. So if you remember what A of t is, the claim is that if you set the time argument to I beta over 2, that will just move around that split up e to the minus beta h over 2 and give you just the thermal expectation value of A squared, which for a nice observable, we assume is a finite thing. Okay, but if I put that into my formula, we will get this. And so this integral should be finite. And if omega is negative, this is becoming exponentially large. And really, this is an even function of omega, so I could replace this by the hyperbolic cosine. But what this tells us is that for this this to be finite, that this has to decay exponentially at large omega. And this really is, this really comes from this original formula being maybe not the smartest way to have written it. Here, the exponential prefactor was taken to be e to the minus s of the average energy. But if we square this and start summing over the intermediate states, the sum over intermediate states will have an e to the plus s of e at the higher energy. And at higher energy is higher entropy. And so that will just exponentially overwhelm this. So if we want to apply this formula where we do things like square it and sum over the intermediate states, this is wrong, right? This was not the right ansatz in some sense. But the f function can come to the rescue and fix it by decaying exponentially. Okay, so there's a limit on the behavior, on the frequency behavior of f, which really just follows from saying that a sum over intermediate states in a square of A should come out finite. Okay, so this gives us some physical intuition about the f function, at least if you have some physical intuition about a correlation function. Now, starting a few years ago, there was a great deal of interest in 4-point functions at different times which were out of time order. So one can define an out of time order correlation function leaving myself some spaces here. And the spaces, again, we're going to do a regularization here where we oops, 4. So I have 4 of them now, so I need an e to the minus beta h over 4. Okay, so this is, again, regulated in the same way that F2 is regulated. This is a regulated correlator. In principle, we could assign 4 different times, maybe start with 0, and then we could have T1, T2, and T3. Those could all be different. But the interesting thing to do, or an interesting thing to do, is to go from 0 to T, and then, if you like, backwards in time to 0, and then back to T. The final answer, so as you probably know, in this case, there was a lot of discussion of an exponential growth period, which I will come to. And there's a bound on the exponential growth rate. That bound depends crucially on how we do this. If you just put an e to the minus beta h in front, the bound, to best of my knowledge, goes away, and there is no bound anymore. Well, I haven't really put a bound on, I didn't try to put any sort of bound on the 2-point function. Yeah, so if we put an e to the minus beta h in front, we would get extra factors like this here. Yeah, so. Okay, and so many of you will know out-of-time order correlators first appeared in 1969 in a paper by Larkin and Ovchinnikov, and then basically disappeared from consideration until 2015 or so, when consideration of them was revived in the discussion of black holes and ADS-CFT and the SYK model, which was considered a simple model of some of the same phenomenon. Maldacena, so let's see, I guess I should say that in systems that have a suitable small parameter, and an example in the SYK model, which is a model of n Majorana fermions, n is the parameter. There can be a range of times, an intermediate range of time, I'll go ahead and call it. So there's a small parameter. Other models have other small parameters. This n is not the n of large n in my general ETH presentation. This is some parameter of the model. People have discussed models that have semi-classical limits where this small parameter is an effective h-bar. And of course, this can't go on forever, because if it went on forever, f would become arbitrarily large and negative, which can't happen. So there's an intermediate range of times, in principle, in which there's an exponential growth period. And famously, Maldacena, Schenker, and Stanford, using various arguments, claimed that lambda was bounded above by 2 pi over beta. And they called this was the title of their paper, A Bound on Chaos. Yes? N is large. Yeah. Sorry? Oh, 1 over n is small, n is large. How about this? There's some parameter epsilon. Oh, yeah, right. Sorry. N, 1 over n, who can tell the difference? Thank you. That was a typo. To the best of my knowledge, if you just throw in a single e to the minus beta h, you can prove nothing. How am I doing here? Okay. Well, when this paper came out, I found it very annoying because, they called it a bound on chaos, and I thought, well, to me, chaos means the ETH ansatz for matrix elements, and so I should be able to derive this bound from the ETH ansatz for matrix elements. And I tried to do that, but I couldn't do it. And so that was annoying. But finally, Laura Follini, who's here, and Jorge Kirchen wrote a very nice paper in which they explained what I now believe is the correct way to think about things like the think about the Rij quote, random matrix elements, their basic point well, first of all, many people thought of the RIJs as Gaussian random. I sort of always knew they couldn't really be Gaussian, but I never thought about what they should be instead. A better way to think about it is suppose we diagonalized A, and we had an observable with some eigenvalues. We can think of a unitary transformation from the energy basis to the A basis as being, of course, given just by this inner product. And Laura and Jorge said, you should think of this as a quasi-random unitary matrix. You don't really want to think of it as a completely random unitary matrix because you should probably have some locality in energy. It probably shouldn't mix up very high and very low energies. So this is some sort of quasi-random, quasi-local. I don't know. Obviously, this is, this is a vague idea, and well, I don't want to say something negative. I'm trying to say that we should think of the random thing as this unitary transformation, but maybe it shouldn't be a completely random unitary transformation. It should have some sort of locality in it. All right, and this I think is really the right way to think about where the randomness is, that you should think of it in this unitary transformation. And once you've decided that, then you don't have to think of these R's as Gaussian. Well, I've erased the 4-point correlator, but if we plugged in the matrix elements in that 4-point correlator, which had a trace, we would end up with a product of 4 R's where the indices go like this because they're being product and traced. Okay. And now if we think of the statistical average of this, if they were Gaussian, we could then express this in terms of Wick contractions, and we could contract them like this, and that would give us a delta IK, or we could contract them from like this, and that would give us a delta JL, or there's another way we could contract them, but that would give us 2 Kronecker deltas, which we can think of as being implicitly in the other ones anyway. And so this is what you would write down if you thought they were Gaussian. But if you believe this, then 4-point functions would just be products of 2-point functions, and that can't be right. Okay. So what they said you should do in this case, and they actually give a much more general prescription, but I will write it down for this case. Is that there should be an additional exponentially small correction. And then there's another function which is analogous to the F function where E is now the average of the 4 energies, and these omegas are 3 energy differences, the 4th being fixed, a linear combination of the others. Okay. So in the sense of looking at individual matrix elements, this is an exponentially small correction to these Kronecker deltas, and you might think that's exponentially small. Why should we care about it? But we are not just, if we don't just look at the matrix elements, but we want to insert them into this correlation function and, along with all the other stuff, do the sums. A Kronecker delta eliminates one of the 4 sums. But remember that each sum we're going to eventually convert to an energy integral which will have an e to the s. So a Kronecker delta actually eliminates an e to the s. And so this eliminates an e to the s by putting an e to the minus s, but that's at the same level of contribution. So this is, when you do sums, this is just as important as these. Okay. So now we can attempt to use this to set some restrictions on how the 4-point function works. And this is some work I did with my then student, Chaitanya Murthy, spell it correctly. And so just like we were able to argue that the f function had to fall off at large omega, one can use a similar argument, again, assuming that trace e to the minus beta h to the 4th should be finite. After a fair amount of work, one can show that this implies that the g function has to fall off similarly to the f function, where, well, let's give it a name. Omega 1 is going to infinity with omega 2 and omega 3 fixed. This has to fall off exponentially. And it's basically the same argument as for the f function, except it's got more technicalities. Okay. And now this behavior of the g function, when we figure out how the g function enters the out-of-time order correlator, this plus a whole bunch of technical assumptions, which I don't want to go into because they are technical. This allows us to put the bound, to reproduce the bound on lambda. So the bound on lambda can be reproduced from a relatively simple bound on the behavior of the Fourier transform correlation function and the finiteness of something like this. Now, when we wrote our paper, we said, okay, this shows how ETH reproduces the bound on chaos. Because we were using the basic ETH ansatz and putting in corrections that have to be there from the correct way of thinking about the transformation. But afterward, we realized that this really does not have very much to do with ETH, because once one has decided that you're going to compute correlation functions with trace e to the minus beta h in them, even if your off-diagonal matrix elements were sparse or had some sort of structure other than the ETH structure, they would be subsumed into some similar statement about a function. So that it was ETH really didn't matter so much. So I think this is really quite general. And more recently, a very nice paper by Laura and Jorge and Sylvia Papalardi has appeared where they relate possible exponential behaviors both in this regulated correlation function and more traditional correlation functions, which also comes to the same conclusion about this bound in the regulated one. And there's also some very nice work which I actually didn't know about when we wrote our paper by Masahito Ueda and his group, which appeared a little earlier, which also does a sort of general analysis that comes to the same conclusion. So the bound on chaos seems to be a very general bound, to me anyway. I'm not sure everyone agrees with that. Seems to be a very general bound in any situation where you can get an exponential growth at all, which requires this small parameter. Yes? It means, all right, so Laura can tell us if she agrees with this or not, since it's her idea. But the way I think of it is that if we actually wrote down this unitary matrix, it would be approximately banded. That is, it would be so here's a bunch of energy levels. It would be mixing up nearby energy levels, but it would not strongly mix energy levels that are far apart. I don't think we know if this is really true or not. It's just an intuitive thing. And for this, it doesn't matter. The real statement is you should not expect the R's to be Gaussian. Okay, that's a sort of negative statement, but not only should you not expect them to be Gaussian, here's the form of the correction to Gaussian. And what Laura and Jorge did was explain, what the correct factor of e to the power of e to the minus s should appear, and they do it very generally. So, yes. Yeah. It really did require a small parameter.
I mean, to get that as written, you need a small parameter, but before that, there's just some result about the derivative of the four-point function with respect to time, and a bound on that. And so I'm wondering if that is also something you could reproduce from non-Gaussian.
In our paper, we went into some detail about the differences between our result and their result. It's a little technical and complicated, and I don't remember it well enough to reproduce offhand. There are some differences. They did have to make an assumption that I claim we don't have to make that required the small parameter. Anyway, I encourage you, if you're interested, to read the details. But both proofs involve various technical assumptions that one has to manipulate. Okay. Let's see. Did I have anything else to say about? Okay. This is really all right. I'm at a stopping point. Next time, I want to talk about entropy and the 5,000 different versions of entropy that there are out there, and how they relate to each other and relate to some of these ideas. But this is all I wanted to say about these 4-point functions. So I think I will stop here for now.
They did remark about the reaction of this exponent power to intercept and high energy scattering, right?
I'm sorry, say.
They did remark about connection of this exponential power to intercept in high energy scattering. Do you understand this? So how it can be understood with your ansatz for this operator? Do you have any ideas how it can be related?
I'm still not clear on what things you want me to relate.
Okay. So they did remark that this exponent power lambda is related to intercept in high energy scattering.
Oh no, I have no.
Okay. That's okay.
No, I have no insight into that.
Okay.
More questions? So, but this, the lambda is related to chaos in some way, right? It's the Lyapunov exponent or something.
They call it a Lyapunov exponent. if I was allowed, if I was made king of names in physics, I would not call it a Lyapunov exponent.
But is it the case that if lambda is greater than 0, the system is chaotic or something?
I'm going to go with no, because I think people have found systems that are explicitly not chaotic that have periods of exponential growth in certain correlation functions. So the connection between this and chaos, I think, is a little tenuous.
Because you mentioned that for interacting integrable systems, you would also have a G of E, which is
Yes, yeah. So
and
I think
then-
you always have a G of E. So it's
and then
unclear to me.
yeah,
If I had to bet, I would say the connection to chaos is really not there. But this is just a very general rule that follows from, it's like the energy time uncertainty principle in some sense.
Questions? Online, are there questions? No.
Just from curiosity, you mentioned this word by Larkin, where this author appearing first. What was he doing?
They were doing something with superconductivity, and it's a very technical paper, and they're trying to compute something. And this structure appeared, and then this idea vanished from the Earth for 30 years. So, I mean, it's interesting because, and this is the kind of thing one might have thought of in quantum chaos theory that people would have looked at. But to the best of my knowledge, this notion did not enter into that.
Sorry, just continuing on this naming issue. So, so you're saying that the behavior is maybe generic to quantum systems, but shouldn't one think that maybe higher values of lambda close to the bound are more typical of chaotic systems and low values? Is that true, or?
The short answer is I don't know. I mean, to put it, the way Larkin and Ovchinnikov originally thought of it was, you could, I mean, they thought of it as a. So if we take the commutator of, say, let me try to get this right. So we could take a commutator of A of t and A of 0, right, and square that. And I think we need a minus sign, and this will have the out of time order thing, and then some other in time order things. And then they said, well, the commutator is like IH bar times a Poisson bracket, and a Poisson bracket grows like a Lyapunov exponent, a real Lyapunov exponent, or might, depending. Okay. And so we could get this, but so now we square it with the minus sign, and we get something like h bar squared. Okay. So, but then this combination. This is what's called lambda over here, and this was thought of as a quantum Lyapunov exponent. So there are situations where this can be connected to a real Lyapunov exponent. I would prefer that Lyapunov, that name was kept for the original concept, and we called this one something else. But that ship has sailed, and everybody calls this the quantum Lyapunov exponent.
More questions? So if not, we thank again Professor Srednicki. So next lecture will be on Friday at 10 a.m.
My problem with this definition is more the opposite, that there are many systems which do
do not have a diagonal that instead have level repulsion
Yeah, no, I
and
mean,
ATH like spin chain or so on.
right.
and,
So this only arises in situations where one has this small parameter,
Yeah.
and